Hello, I'm Stéphane Graber. I work at Canonical. I'm the project leader for LXC, LXD, and LXCFS. Today, I'm going to be talking a bit about LXD and especially what we've been doing recently to make our vision of system containers and now virtual machines as good as it gets. First, we're going to just go over some of the basics. So quickly going through what system containers are. System containers are containers. So that means that they're sharing the kernel with the host. They don't use any virtualization technology. They're also the oldest type of containers. System containers started way back with BSD jails, then implemented on Linux using Linux vServer, which was a external kernel patch. Then a Solaris implementation was done with Solaris zones. And after that, the OpenVZ project implemented them on Linux again in a more comprehensive way than Linux vServer, but that was still a pretty big patch on top of the Linux kernel. Then came LXC, which was the initial tooling for driving the native implementation of containers in the upstream Linux kernel. And finally, LXD, which is what we have right now, which is a pretty complex, featureful daemon that can manage many containers using a clean mainline Linux kernel. Now, to kind of differentiate application containers from system containers. System containers really behave like standalone systems. In many ways, they behave like a physical system or a virtual machine. There are no, the images that we have for those system containers will be full Linux distributions. They're not going to be particular, very specific workloads like you might have with application containers. They're effectively just as easy to understand and manage as a fleet of physical machines or virtual machines. So they lend themselves very well to legacy workloads or places where a complete redesign of one's infrastructure to use application containers and a set of stateless workloads is not very practical. Being containers, they're very low overhead and very easy to manage. You can run thousands of them on a system. They just show up as a bunch of processes. It's very nice and easy to know exactly where your resources are going. And LXD does a great job at offering you a lot of tooling to set very specific resource limits and also allow or block a number of devices and actions in those containers. Now for virtual machines. So virtual machines are mostly defined by virtualized hardware and firmware. So you run an entire system in a virtual machine that includes booting its own kernel, but also its own firmware. They are usually hardware accelerated. Virtual machines that are only done through pure CPU, like purely in user space, tend to be very slow and CPU hungry. So most virtual machines are hardware accelerated, requiring your CPU to have dedicated extensions to perform virtualization. That's the case on most Intel CPUs for years now. That's also the case for more recent ARM chips and some other architectures, but exactly how that works very much depends on a per architecture basis, which is not really something we deal with containers, because on the container side, all the architectures, so long as they run Linux, they will behave the same way as far as containers go. The fact that they're hardware accelerated also means that you can do things like physical hardware pass-through. So that means passing through a piece of hardware that the host system might not know how to drive. You can just expose that PCI device or whatever device directly into the guest, and then the guest might have a different kernel and set of drivers that can actually make use of that. And also, pretty importantly, virtual machines can run anything. Containers are limited to running Linux on Linux. You can run very old Linux distros. Like we commonly run things like CentOS 3 on top of a very modern Linux distro using one of the latest Linux kernels, and that works fine. But you can't run, Windows or BSD or any other operating system inside a container because it's a different kernel. Virtual machines don't have that limitation, so they are quite well suited for things like running a completely different operating system or doing operating system level development or changes. So say you need a custom kernel module that you don't want to load on your host system, you can totally do that in a virtual machine, whereas it's not possible to do that in a container. Virtual machines do, however, come with significant overhead as a result of that. Even with hardware acceleration, you might be able to run, tens, hundreds of virtual machines on a system when you could run thousands or tens of thousands of containers. It's simply because even an idle virtual machine will still have to handle a number of interrupts, and you need a number of context switches to those different virtual machines, whether they're doing something or not. Now for what LXD is. So LXD can be seen as like a pretty user-friendly manager for both containers and system containers and virtual machines. It's based on a REST API and has a number of clients that can talk to it. In the demo later, we'll mostly use our own client, which is our command line tool, but a variety of others exist. It acts in many ways like a tiny local cloud, effectively. Everything is image-based. It's very fast because it can make use of optimized storage to prepare the volumes and then very quickly create more instances from those volumes. It knows how to drive a lot of complex things like resource limits, driving a variety of storage drivers, driving a variety of network options. It can drive containers and virtual machines through the exact same API and exact same tooling. It's also designed to be safe by default, so we use just about every single kernel security feature we can find all together from the start to make it just as safe as it gets. And it's pretty scalable. You can start with a single laptop deployment that can be installed and up and running in seconds, to scaling that to very large clusters of potentially 50 to 100 individual physical systems that are all clustered together as part of a larger LXD deployment. LXD itself is written in Go. It uses libxc to drive the kernel layer part of containers, and it uses QEMU to drive virtual machines. It exposes a REST API for its clients to consume. There are no other APIs, so there's anything that our command line tool can do, you can do it through the REST API, because that's all that it does. There are a number of bindings in some languages for that REST API, and as I mentioned, a variety of clients that you can use too. As you can see here in the diagram, just shows multiple LXD systems, all running Linux, all with libxc and QEMU to run the low-level workloads. Then LXD sits on top of that. It exposes the LXD REST API, and then you can have clients that talk to those different systems. Now, quickly going through some of the main components of LXD itself. So we have obviously the main part is gonna be instances. So that's kind of what you see in the middle. That's containers and virtual machines. They themselves have snapshots or backups that can be made automatically or on demand. Those instances have been usually created from an image. Images can be stored locally in an image store. And you've got aliases on top of those images to make it easy to find them by name. You also have a storage layer, so a number of storage pools, each of those with storage volumes, and each of those storage volumes potentially with snapshots. Those are created for images, they're created for instances, but you can also allocate your own storage volumes to attach to one or multiple instances. And instances are also connected to network, and Nextday has an API that lets you create and manage network bridges directly. Now, for multi-user systems, it's often a good idea to have independent view of the entire thing. And that's what projects let you do. So with projects, you can create your own isolated view of Nextday that each can contain things like instances, images, custom storage volumes, and soon networks. That makes it easy to avoid any potential clashes with like two different tools, two different users talking to the same system, but wanting to use the same name. And they're getting conflict. Instead, you can just create multiple projects and have them use their own project. Internally, we also have some other APIs like certificate management for access, the event API to be notified whenever something happens in Nextday, and operations for long-running background operations and their status. And there are a number of other smaller APIs not listed here, things like file transfer, executing of commands, getting access to console, or turning instances into images. Are all of the endpoints we've got in there. Now, another thing that's kind of interesting is starting now a few years ago, Nextday is quite commonly found on Chromebooks. In fact, all new Chromebooks selling now come with Nextday support and can very easily get a user into a Nextday container. That's listed as the Linux on Chromebook feature. And when you use that, it gets you into a Linux shell where you effectively get a normal Debian system. You can install a number of applications you want. Graphical applications are automatically integrated into the Chrome OS shell. So you can just look for them as a normal application and install it or run it from there. It's got integration for things like snapshots, backups, file transfers. They also do USB pass-through and GPU pass-through, all directly integrated in that Linux experience on Chromebook. Another place you might have seen or might have interacted with Nextday, even if you didn't really see it, is on Travis CI. Travis CI, I believe last year or a bit before that, rolled out support for additional architectures. That was support for ARM64, PowerPC 64-bit Little Endian, and IBM Z, the S390X architecture. They're all now supported for jobs on Travis CI, and all of those runs inside Nextday containers that are created on demand and then thrown out as soon as the CI job is done. That's done to avoid having to deal with virtual machines on those architectures, especially because some of the workers for those architectures are actually virtual machines themselves and can't nest virtualization. So that's giving very, very quick, a very quick experience to very quickly create those instances and then get rid of them later. The average instance creation time we've seen is somewhere between like 2 and 5 seconds for a new instance to be created and running, whereas some of the other platforms they used in the past for Travis used to be public cloud-based and would take upwards of 40 seconds. So that also increases density and the amount of jobs they can get through a day by quite a bit. Now, going through some of the features we've got around system containers first. So that's really our area of expertise. I mean, the entire Nextday team are container people. We contribute to the Linux kernel. We've done a lot of the design for a lot of the features that are currently associated with containers in Linux. And we think that our implementation of system containers is definitely the best out there right now. And some of the strong points we have are resource limits. So our containers can have a limited amount of CPU applied to them or memory. Network and storage bandwidth can also be restricted. Number of processes can be restricted. And then a wide variety of additional kernel flags can also be set for limitations on things like number of open files and shared memory and a number of other things can be restricted there. It's got pretty wide device pass-through support. So we support passing things through like additional network devices, whether they are virtually attached to a bridge device or they're physical NICs attached to a physical network. We also support attaching disks, so that's either a straight partition or a shared volume or even a shared path with the host. Also support things like GPU pass-through, which lets you access the host GPU, especially for compute. Then we've got USB pass-through as well, which exposes USB devices to the container. That's most useful for those devices using libUSB. And we also have effectively like a blanket way of passing through any device that's got a Unix character device or Unix block device on the host directly into the container. Sometimes it's dangerous to do so, so it's really up to the user to pick the right ones. But it's very flexible, and unless you do just about anything from inside the container, like you can do home automation by accessing some random serial type interfaces. You can access scientific equipment. You can access just about anything. And we've got quite a few advanced features, mostly based on the work we've done in the kernel space. So we contributed to work done by Taiko Anderson on system call interception, which then lets our unprivileged container selectively do more privileged tasks, things like mounting some specific file systems that would normally not be allowed, or creating some specific device nodes that would also normally not be allowed. That work was quite critical for things like Travis to work properly, because that lets us very specifically enable features that a normal user is normally not allowed to do, but that we feel are actually safe to do in some cases for some containers. We also support event injection, which is also logic we've added to the kernel a few years ago. That means that when you pass through a USB device, for example, to a LXD container, the associated hot plug event is also passed into the container. For security, we've added support for isolated ID maps. That means that no two LXD container, when that feature is enabled, will ever have any overlapping UID or GID, which eliminates an entire class of denial of service type attacks that would otherwise be possible if any UID or GID is shared between containers. And lastly, of the things to mention here is ShiftFS, which is effectively an overlay type file system we implemented, which allows for such isolated containers to still share data between them, effectively by mapping UIDs and GIDs between their independent maps, and also easy sharing data with the host without having to rely on either manually shifting or complex ACLs for access. On the virtual machine side, so that's still quite new for us. We've only been doing virtual machine for less than a year, like we're looking at maybe 6 months or so since we first landed usable code for them, which is actually quite a bit of an advantage for us. As we're coming late in managing virtual machines, it means that we could go with a legacy-free approach and just look at what we expect modern virtual machines to need and use, and not do any of the legacy device emulation or any of that stuff. So legacy virtual machines are pretty modern. Whenever possible, we use UEFI with Seccomp and a modern PCIe-based machine type whenever possible. The devices we expose to the VM are usually all virtio-based, and we use a very recent QEMU version as well for that, which has some nice advantage in how we can pre-generate the config and validate it ahead of time. Now, as far as user experience, one thing that was quite critical for us was that we wanted virtual machines to work just the same way as containers, and they do. So there's no special VM API or anything. By and large, the limits and devices and all that stuff that we have on containers just are virtual machines as well. And we even run a agent inside the virtual machines, which then lets us do things like file transfer and executing commands and all that stuff exactly as if it was a container, even though it's a virtual machine. So it's really quite nice in that our API users could effectively decide to use either a system container or a virtual machine without needing any code change. And all of that also integrates seamlessly with our network and storage layer. They also get tied to profiles and can be stored inside projects. So everything just lines up exactly the same as containers in that regard. We've also added some VM-specific features, so things like support for huge pages and SR-IOV and VFIO. So you can use SR-IOV for networking and use like a virtual function for the network device inside the VM. And VFIO lets you pass either an entire network card through to the VM or pass a dedicated GPU through to the VM as well. We currently have support for virtual machines on Intel 64-bit, ARM 64-bit, PowerPC 64-bit, Little Endian, and IBM Z. And last thing to mention before we go into a demo is LXD clustering. So that's the ability to effectively cluster a number of LXD systems together, have it behave like a single large LXD deployment. So we've had that supported for over 2 years now, probably getting close to 3 years actually. And that's working really quite well. It doesn't need any external services or daemons or anything. All LXD daemons are capable of clustering. It's just one question to answer when setting it up, and you can cluster multiple systems together. Similar to what I said for virtual machines, there is no need for cluster awareness in any of the client tools that talk to LXD. So a tool that was designed to run against a single laptop will just fine against a cluster of hundreds of systems. That's perfectly fine. And LXD clusters can run thousands or tens of thousands of containers on quite a lot of cluster nodes. The database itself becomes highly available as soon as you run 3 or more nodes, and LXD handles all of the cross connections between all the nodes all over the LXD API. And these days we even support mixing architectures, so you can have a cluster that's made of some Intel systems and some ARM systems, and that works just fine. Then depending on the architecture of the image you're trying to launch, the right cluster nodes get selected. All right, so that's enough talking for now. Let's look at that stuff a bit. So let me just switch over to a terminal. There we go. And we'll start by just installing LXD. So let's do that. So in this case, we're using the snap package because that's the easiest way to install it on Ubuntu. There are native packages on a number of other distros too. I mentioned ShiftFS earlier, so we'll just enable it there. That makes things a tiny bit faster and more interesting later on. And then we configure LXD. So that's that LXD init command. We will not be doing clustering on that system, but we do need storage. And it will default to using ZFS. It's fine. We do have a dedicated drive we can use on that system. It's an NVMe SSD, so let's use that. And the rest we'll just use the defaults because they're perfectly fine for what we want. And that's it. LXD is set up. So let's start by running a Ubuntu 2004 container. So it's downloading that image, it's unpacking it, creating a new ZFS dataset that can be cloned, and then the container is started. We can get a shell in there. And let's look at what we've got. So it is Ubuntu 2004. Now let's look at resources. So out of the box, we see we actually get the entire physical machine. So it's got access to all 24 CPUs, and it's got access to 128 gigs of RAM and to 1.9 terabytes of SSD. Okay, that's fine. Let's launch another container, but this time let's do 2 CPUs and 4 gigs of RAM. So we just apply that at launch time. We can also see that it got significantly faster because the image is already loaded on the system. Now, let's look at CPU again. Okay, we just have 2. Memory is down to 4. Disk space is still 1.9 terabytes. Let's change that. So we'll just override, oops, typo. Just override the size to 2 gigabytes. Go back in. And we're down to 2 gigabytes now. One thing that's worth mentioning is that all of those resource limits can be all changed live. There's no need to restart any container or anything. So now we can see those 2 containers running. We'll see their IPs. And we see that snapshot column, which is currently showing 0 snapshots. We can change that. In this case, we'll change it globally. So we'll make it so that every single instance on that system gets a snapshot per minute. That's a standard cron pattern, so we can do something else. Now, let's play with storage a bit. So here we're going to create a new storage volume called shared. We'll make it shifted, so it's going to use shiftfs to attach it to containers, and we make it a size of 5 gig. And then we will attach it to the default profile, making it such that any instance using a default profile will get that file system mounted as /shared. Okay, it's done. Let's see if that worked. So we go in the first container. We can see that /shared is now mounted. We see 5 gigs. And write this red bar into a file called foo. Then let's go into our second container and make sure we can see that file. And we can. All works. Okay, so far I showed on the Ubuntu stuff. LXD can do far more than that. So let's do Arch Linux. Okay, so Arch is started, and now let's do CentOS 8 as well for good measure. And just to show that the default profile does its job, we can go check this one. So it should show that it's CentOS 8. Yep. And shared foo is still there. Now we can look at a list of our containers again. We can see that the first 2 have now got their first automated snapshot. Okay, so that's containers, kind of basics of how containers work on LXD and resource limits. Now let's do virtual machines. So we'll be doing this. That's Ubuntu 2004 as a virtual machine. You can see an extra --VM flag, and we'll pass it 8 CPUs and 32 gigs of RAM. This is once again downloading an image, which is different than a container image. It's also a bit larger, so it will take longer to unpack. But similarly to containers, if we create any more virtual machine from that image, it will be significantly faster. Should start any second now. Trying to remember how large the Ubuntu image is. It's probably 500 megs or so, whereas the container image is, I think, under 100 megs at this point. It's just the virtual machine images tend to be quite a bit larger just because of having to ship an actual file system instead of just compressed files, and also because they're shipping a kernel and firmware and bootloader and all of those bits. That quickly adds up. Okay, finally. It was a bit slower than expected. So now it's created and it's starting it up. There we go. Okay, let's just create a second one. And while that is running, so that second VM will be based on OpenSUSE, Tumbleweed, and disable Secure Boot because OpenSUSE doesn't interact well with Secure Boot right now. We'll just get a second shell back on that system while that's going on. And we can just go look. So let's do the console, get the console on that first VM. You can see what at a login prompt right now. So that's all good. If we list things again, we should see V1 is running. We also see its IPs, and we see that V2 is being created right now. We also see that V1 already got its first snapshot. Let's get a shell into v1. So it looks exactly like containers. You can see /shared is working fine. Let's see how wide it is. Should see 5 gigs. Come on. I guess that unpacking is quite taxing. There we go, 5 gigs. And we can look at the PCI. Is it PCI utils? Oh yeah, there we go. Just show the PCI layout in there. We can see that pretty much everything is virtio based, except for the most basic motherboard emulation bits. By now that v2 VM has actually started, and we can see it's also working just fine. So now there's an OpenSUSE system, and we should still have our file working there. I can see the expected content. So that's now a shared disk between several containers and several virtual machines on the same system. And lastly, let's create another virtual machine, also from the same image, so that should be pretty quick this time. There we go. And this one will make it a bit different by giving it an SR-IOV network card. So launching should take, while starting up, should take a bit longer this time because it needs to actually configure the physical network card to give it a physical slice. And that slice is then attached to the virtual machine. Okay. And take a look at it booting. Okay, so it's starting up. It's done. So let's just get a shell. Ah, right. Keep forgetting that this is not installed by default. Okay. So if we look now, we see that last entry shows an Intel Corporation Ethernet controller. So that's the physical network card that was passed into that virtual machine using SR-IOV. Okay, so that's enough for just showing containers and VMs on LXD. Let's just take a very quick look at clustering. So I'm on my laptop now, and I'm just gonna interact with a remote LXD. So that's the syntax in our command line for that. Here, that remote is called s-rpi, which is a Raspberry Pi based cluster. You can see it's got 3 nodes, and they're all ARM64. There should be some existing workloads on there. Yeah, we can see 3 virtual machines running. Let's say that we now want the Ubuntu 2004. Let's do a container this time just for a change on that. So we just do this. And that instructs that Raspberry Pi cluster to go and download a suitable image, unpack it, and then start a container called C1. In a cluster, the least busy node is always taken for the container creation or instance creation, so also virtual machines. So in this case, given that they each already have one instance, I would probably expect cluster 01 to be the one getting it. Yep. And we can see it's started up, it's got an IP, and we can get a terminal inside it, and we can go and look at the architecture. We'll see what indeed on ARM64. So that's basic LXD clustering. One last thing I want to show is we actually have GUI access now in LXD virtual machines. So I do have a virtual machine locally called Win10, which is not too surprisingly Windows 10. So we can do -- console equals VGA while starting it. And let me just move that window across so you can see it. There we go. So that's what happens in that case. You can see we're connecting to the screen of the virtual machine directly, and we can see that Windows system booting up. You can also see that we've got our custom firmware here running. So it shows the LXD boot logo while Windows is loading. Should just take a few seconds and get into the login screen for Windows 10. We obviously do not have pre-built images for Windows because it wouldn't be legal to distribute those, but we do have a tutorial on how Windows can be installed from scratch from standard ISO, and then can be and then can be turned into a LXD image, so you can locally create then as many Windows virtual machines as you want very quickly from that image you've manually created. We're also working on tooling in our image management tool to let you easily convert existing Windows 10 virtual machine images that can be found on Microsoft's website into something that can directly be consumed by LXD. That should make it quite a bit easier as well. Yeah, Windows always takes its time to log me in somehow. Let's give it a few more seconds. If that doesn't work, or if that's not done yet. Oh, there we go. Alright. So yeah, that gets you Windows 10 running inside LXD. In most cases, the graphical console that LXD can get is not the best way to interact with virtual machines. For Windows, connecting over RDP is quite a bit better, but it's a good debugging tool to connect and see what's going on the console, especially for things like Windows, where you don't actually have a text console that you can use. They just don't implement that, so you only have the graphical console. Okay. And that's it for the demo. Just switch back to the slide. Okay. And just to wrap things up, I'll just quickly recap what we've seen so far. So system containers or virtual machines, it's really up to you now with LXD. Both of them are supported and work pretty much identically. It really depends on your workload. If you need to run a different operating system, then use Windows, or then use virtual machines to run things like Windows or FreeBSD. If you are to run the same Linux version on top of the same Linux version, then definitely use containers. There are even different Linux distros, and Linux versions work just fine. And it's all, you can easily scale from a pretty simple test or experimental environment all the way to pretty large scale production. That's what we can do with LXD clustering. It's very easy to connect multiple LXDs together. Like in this example, it was 3 pretty affordable Raspberry Pis connected together in a cluster. If you want additional fault tolerance in a cluster environment, you can also use replicated distributed storage. We support Ceph in that case, and that tends to be a good combination for both LXD clustering and Ceph to get you the most reliable environment. There's very easy storage network, GPU, USB, and generic device pass-through in LXD. You can easily expose that hardware to containers and, when possible, to virtual machines. And you can use quotas and limits against those instances to prevent any abuse. LXD itself works pretty much everywhere, so the daemon itself needs to run on Linux, but can run on any Linux distribution. The snap package itself is tested over a dozen different distros daily, and there are native packages in a number of other distros. The client tool itself also works on Windows and macOS, so you can just run the client tool natively on those platforms and then interact with the remote server that's running Linux. And it's all production ready. We've got long-term support releases that come with 5 years of support. LXD 2.0, 3.0, and 4.0 are currently all 3 LTS releases that are still actively supported all at the same time. And otherwise, we do monthly feature releases if you just want to live on the bleeding edge and get the new features every month. LXD itself has been around for over 4 years now, coming up 5 years. And LXC, which it uses for which we develop and which it uses for management of containers, has been around for over a decade. For more complex production environments that also have access control in mind, it's possible to integrate with an external role-based access control system that Canonical provides to some customers. But everything else is just available out of the box, and you can do your own thing very easily. And that's it. So I hope you found this interesting. You can go on our different websites listed here. One of the interesting ones is the third one, which is the online demo. It lets you play online directly from your web browser with your own copy of LexD for 30 minutes. It's just takes a second to start, and it's quite a good way to just play with it before you really decide to install it anywhere else. And that's it. Thank you very much.